So this PT video is on the photon model of radiation and the idea of intensity. And what we're going to look at first of all is what is a photon. So to do this properly, we need to look at what this sort of old picture of electromagnetic waves was before the idea of the photon came along. And that's just a single sort of continuous wave, and that's called the classical wave model of electromagnetic radiation. And the idea of what matters in terms of the rate of energy transfer was the amplitude of the wave and the frequency of the wave. If we increase either of those two things, then we get more energy transferred by the wave every second. Okay, so the photon picture looks a little different. What we do is we have all of these little sort of bits of the wave, which we call photons, and you need to think of the photon as like a packet of energy. It's got a certain amount of energy that it carries with it. Okay, so the rate of energy transfer in this model depends on the number of photons arriving every second and how much energy each photon carries, the energy of a single photon. So in some ways it's a lot easier to kind of visualize than the wave model, because relating amplitude and frequency to energy is tricky. Whereas if you think, okay, each photon carries a certain amount of energy, so the more of them there are every second, the more energy will be transferred, and if each one's carrying more energy, then there'll be more energy transferred in total as well. So the photon picture is quite useful for thinking about energy transfer and waves. Okay, so how do we relate that to intensity? Well, first of all, we need to know what intensity is. And it's basically a measure of sort of looking at how strong or how bright the electromagnetic radiation looks. And the technical definition is that it's the amount of energy arriving in an area of 1 meter squared every second. So the things that matter for this, if you like, are how much energy there is in total and also how concentrated it is. So if we focus the energy down into a smaller area, that will make it more intense. Okay, so let's imagine we have a light source and we have light coming from it. And so we're just looking at what the intensity looks like at different distances from the light source now. So if we go further away from the light source, the intensity drops. That makes sense because you experience that. If you're further away from a light, it looks less bright. So we get high intensity relatively near the source, and if we go further away, we get low intensity. So we need to be able to explain that, and in terms of what's going on, the energy gets more spread out as it moves away from the source. So less energy arrives in every 1 meter squared of area. If we imagine each of those squares on the diagram as a meter squared, then the blue lines are just showing us where the energy is going. Now obviously the light comes out in every direction from the light source, but we're just concentrating on some light coming in one particular direction. The energy that went through that original 1 meter squared at the high intensity close to the light source here has been spread over 4 times as large an area when we go to twice the distance. Okay, so you can see that the intensity is going to be much lower because we've got the same amount of energy but spread over a larger area. Okay, so each individual 1 meter squared gets less energy moving through it. And the other thing that can happen is that some of the light will be absorbed by the air or gases in space or anything that it's travelling through, and that will further reduce the intensity as we get further away from the light source. So those are the two things that can reduce intensity. So that's like the classical picture, just looking at the energy. How does this look if we look at the photons? Okay, so let's take out the sort of light and just put the photons back in. So let's imagine we've got 8 photons in every 1 meter squared when we're near the source. Okay, what's going to happen to those photons as we get further away? Well, we'll get 2 photons in every 1 meter squared. The 2 in the bottom right corner will end up in that square. The 2 in the top right corner will end up in that square. Top left corner, those 2. Bottom left corner, those 2. Okay, and the reason I've put less than 2 photons in every 1 meter squared is that obviously some of them may also have been absorbed on the way, so we may get even less than that. So that's the idea, and you can see what happens here is we've gone from 8 photons in every meter squared every second to 2 photons in every meter squared every second. The individual photons are carrying the same amount of energy, there's just fewer of them going through each meter squared, and so the intensity is less. Okay, so the photons travel in a straight line from the light source. They get more spread out as you get further away from the source. Some photons may be absorbed on the way, reducing the intensity further. That's how we explain the fall off of intensity, the decrease in intensity as we get further away from the light source using the photon model. The final thing we're going to discuss when we're talking about photons and intensity is looking at sort of comparing beams of radiation. And this question has come up a couple of times and caused some confusion. So I'm just going to give you an example of this and talk about some of the things that you might not need to worry too much about and the things that you do need to worry about. So let's just look at an example of like a laser beam. Now a laser beam keeps a high intensity as you get further away from it because its light doesn't spread out. That's the characteristic of a laser beam, or something like a searchlight beam as well. The light stays parallel and doesn't spread as it goes further away. So the only thing that could decrease the intensity there would be the absorption. We're going to ignore that as well and compare these two beams of laser light. So I'm going to start off with a beam of light that's got red photons. So it's red beam of light. And if you remember the electromagnetic spectrum, then we say that the sort of radio microwave end of the spectrum is very low energy. When we're talking about energy, what we really mean there is the energy of the individual photons. In a similar way, the red part of the visible spectrum has lower energy compared to the sort of violet end of the spectrum. So if we were to look at the energy of the photons for red, it would be low, and the energy of the photons for violet, it would be higher. Now, don't worry too much. This is one of the things you don't need to worry about the units of energy. These things called EV. I've put these in there because they might use them. You don't need to know what they are. You just need to understand that, obviously, if a photon has a higher number of EV, then it has more energy. So, the red light photons, 1.8 EV each. The 2.7 EV photons are the purple ones at the bottom. Okay, so how do we work out how much intensity there is in these beams? So remember, the rate of energy transfer is the number of photons per second multiplied by the energy of each photon. So let's imagine these beams of radiation, that's a second's worth of light arriving. In a real beam of light that's of any sort of reasonable intensity, the number of photons will be massive. It will be billions upon billions upon billions of photons. So we're just using this as an example, okay, to keep it relatively straightforward. Okay, so let's just work out what the intensity of these beams is. We just put the information into the equation. Now, this equation is not on the formula sheet, so you need to remember this. So the rate of energy transfer, there's 6 red photons there, so 6 times 1.8 each, so 10.8. I haven't put the units in. It would be 11 electron volts per meter squared per second, if we were assuming this beam of radiation is hitting a meter squared of area. Okay, so the purple beam then, same thing. We've only got 4 photons, each of them 2.7 electron volts, and we do 4 times 2.7 gives us again 10.8. So these two beams have the same intensity, even though they're different colours and there are a different number of photons in them. Because the two factors kind of cancel out, in this case, you get the same intensity of radiation. They have asked this question, but ask you to sort of fill in either a number of photons or the energy of each photon in a little table. And all you need to remember is that the intensities are the same, then the energy times the number of them will be the same. Okay? And that's how you use that information. So, just to recap, the formula for this is not on the formula sheet. Don't worry too much about the units. And the last thing is that this is an example of a place where you might have to use standard form. If they use joules for the unit of energy of the photon, for example, then that will be a tiny, tiny number. Okay, so you'll have a number that is sort of 10 to the power of minus 19 joules would not be unusual. And similarly, if they use any sort of normal intensity, then the number of photons will be gigantic. And so you could have, 10 to the 20, 10 to the 30 photons in the beam of radiation every second, and that would not be ridiculous. So make sure you know how to use standard form on your calculator so that you can put the numbers in for that. Okay.